We'll be working on page 535. This is Introduction to Trig, and such a huge concept. To be ready, you're going to need something to write with, some markers for highlighters, and definitely you're going to need a ruler, something that you can measure in either inches or centimeters that you can help with our calculations today. And a calculator. So I'm going to use like Desmos, or I'm going to use my phone calculator as well to get that done. Let's talk about this one though. In this video, this is such a huge important concept in geometry, and we don't save it for last, we just build up to it because it's gonna be coming back in Algebra 2 and pre-calc and calculus and even like the life skills of things that you're gonna need to know. So let's get into it. Trigonometric ratios are built upon four things: a reference angle, identifying the opposite side to that reference angle, the adjacent side, and then the word trigonometry, but there's also the word hypotenuse. That's not in this, but I'm going to add it. Hypotenuse. You got to know those four things, and then it's all part of the concept of trig. You got to know those four things in order to be able to do trig. Great stuff on the first page of our lesson here. Great stuff on the second, but let's get right into what we need to do. The goal is to explore and understand what we get from trig ratios, what we get from the sides of a triangle. Now, with me, let's highlight some key things. So I'm first of all going to highlight that in this one, the 45-45-90 triangle, there are two special types of triangles that we're going to, just two that we need to know about, but we're going to establish the idea of making ratios, fractions, out of the sides of a triangle. And the two triangles we're going to use, one is a 45-45-90 triangle. Okay, 45, that's the reference angle. So I'm going to put a little like circle mark there, and then I'm going to use what's called a theta. So Theta. It's an O with a belt. It's a Greek letter. You know, most of our alphabet does come from the Greeks, and when we ran out of ABC, XYZ letters for math, we started jumping over to where geometry came from. The Greeks. Well, the Greeks really did a good job. Thank you, Euclid, for figuring out. So we're honoring the Greeks historically by giving the reference angle a Greek letter. And I'm putting the theta where I did, right on the 45. Okay, there are four things that we need to identify. We need to know where theta is, where the hypotenuse is, where the opposite side to theta, where that side is, and then where the adjacent side. Now, adjacent means next to. So which is the side next to? And I save that one for last because technically, if this is our reference angle, we have two possible adjacent sides. But it's always important to do things in this order. 0, 1, 2, 3. And I say 0, you cannot do anything until you've identified the reference angle. So there it is. Theta, 45 degrees. Now the hypotenuse, that's always going to be across from the right angle. So those are both going to get highlighted yellow. Like you got to do those first. Now, the opposite side, once you know which of these is the reference angle, that's theta, which of these is the hypotenuse, so that's the side, the longest side, it's across from the 90-degree angle. The opposite side is just over here, away from the 45-degree angle, and that leaves us with the adjacent side, side number 3, choice number 3, the line we haven't highlighted yet. Those are always going to be in that like arrangement. From the reference angle, there's the hypotenuse because it's across from the 90-degree angle. There's the opposite side, so I'll put in O for opposite side, and then adjacent side. Theta, HOA. Always in that order. Now, what we're going to do, I'm going to ignore question 1, and I just want to talk about what we get from this, right? So if we have theta, HO, and A, we're going to like measure for this triangle, and I want you to notice something. Maybe like where's some side notes here. This would definitely be worth like a sticky note, and we're going to see it on the back of this page. If you have 3 sides of a triangle, trigonometric ratio means the measure of 3-sided shapes studied in fraction form. That's literally what trigonometric ratio means. Trig for 3, metric as in measuring the distance, and then ratio, fraction. The Greeks loved to discuss things in fractional values. So ratio meaning fraction or comparison. Now we're going to do that. We're doing trigonometric ratios as in we're making three measured fractions. So there are three sides of a triangle. Here's one of the fractions. We can take the hypotenuse. I'm just going to use h for right now. And I can make it be the top of a fraction. And on the bottom, I can make O. I can do another fraction. I can do h and a. You know, if I can put h on the top of a fraction, I can also put h on the bottom. So I can say this is also another fraction that's possible, O over h. Then I can make another fraction where I just take this one. I'm making a fraction of that side length, so all of that yellow distance to this side length, call that h over a. We can also flip it around and go the other direction, a over h. Now we're missing some. I have ho and the flip, OH. I have HA and its reciprocal, AH. So what's left would be OA as a fraction, or the flip, A over O. There are no other fractions, no other trig fractions that we can make other than those 6. And what we'll do in the next few lessons, next few video sequences, is we will talk about their names. These fractions, because there's only 6 of them, they each get their own specific name. And we'll talk a little bit about why. But other than that, you only need to know 6 fractions. There's no other fractions to know. If we're going to do some mathematics, we might as well get some numbers. So setting up with the structure on the next page, let's go ahead and record the side lengths for triangle ABC. Wait a minute. Choose any point along the hypotenuse and label it point D. Then construct vertical line segment DE, connecting AC so that DE is perpendicular to AC, and label the endpoint. Oh, okay. We do need to do this part. So this part is going to help us set up our successful moment in the next couple of lessons. I'm going to pick a point D on the hypotenuse. So roughly the middle, but don't try to be in the middle. Maybe like right here. Now, I know, so we're all on the same page, let me get a measurement on that. That is approximately 2 inches from A. Go out 1, 2 inches, and then put a dot. Now we're going to drop a line straight down from that value. And so I want to be as 90 degree as possible, kind of using like the markings here in the protractor. Oh, I should do it this way. I should extend this line even further out and then put my circle over my triangle and put my 90 degree. There we go. I need a perfectly 90 degree line created right here. Not bad. Okay, so then this part right here is going to be called E, just like they say in the directions for number 1 and 2. I'm trying to create 2 triangles, a smaller triangle inside a bigger triangle, and then we're going to study the information we get from that. Now, because we're going to be doing some fractions, I'm going to jump away from inch measurements and start using millimeter measurements. That means every little single line of the millimeter side of our ruler. So on the next page, here we go. I'm going to label the side opposite angle A. So we labeled that side, and I'm using green for the side opposite angle A. Honestly, though, you should do that in this order. So I'm going to break from the way the table is written. You should do it in this order. You should, first of all, identify angle A is the reference angle. And then you first find the hypotenuse. Label it, name it, use it. The second thing you should find is actually written over here in the very beginning, but you should find the opposite side secondly. Hypotenuse first, then the opposite side, and then the adjacent side. And as we're learning trig, that's the order to follow until you are so good at these and you practice them so many times, you don't need the order anymore. But as far as a recipe is concerned, for now, that's the recipe. Let's find the length of the hypotenuse, and let's do it for the big triangle. So yellow should go first. And for that yellow shape, this is going to be AC. Okay? How many millimeters is it? Okay. Oh, I'm so wrong. I'm looking at my shape again. It's AB. Sorry, if you're using a pencil, amazing. If you're using a pen, you are living dangerously. AB. Okay. Swipe this back. So we're going to measure. I'm going to get 70. Let's see here. Putting the 0 on the beginning and then going in groups of tens. So 10, 20, 30, 40, 50, 60, 70, 71, 72, 73. I want to say 73 millimeters. This entire line from A to B is 73 millimeters. I mean, prove it, right? You should prove that yourself. Now let's do the side that's opposite from angle A. Let's do that one secondly, and that's going to be in green. So we're measuring, let's see, check it again. BC. BC is the side. Oh, it doesn't even use the letter A in the name, right? If it's opposite angle A, you're not using the letter A in the name of that side. And BC, so we're going to measure it. So a ruler comes out, millimeters, mind you, every little tick mark. So setting up here, 0, and then count by tens, 10, 20, 30, 40, 50, 51, maybe 51 and a half if I want to be like, I don't know, picky. But let's round up. Let's say 52. Rounding to 52 millimeters. Now, mm's for millimeter, mm for millimeter. Okay. Last of all is the side length adjacent to angle A. And so that side length adjacent to angle A has to use the letter A. So it's going to check here for a minute. It's adjacent, so it's touching angle A. AC. This is the only combination of letters that we have left to use. AC. And we need to measure this one. Now, I have an idea already of what it's going to be. I'm going to write it down here. Okay. I wrote it down on this paper, and I'm going to reveal this paper. So I'm going to put it over here. I'm going to reveal that paper when we've measured it of what I think it's going to be. Okay, here we go. Measuring. A to C. Get it centered. Here we go. Count by tens. 10, 20, 30, 40, 50, 51 and a half. It's 52 millimeters. Also, that's actually the thing about 45, 90 triangles. 2 of the sides are going to be the same length, and we're rounding. It was kind of in the middle, so we're going to round up to 52. I mean, 51 and a half millimeters. Let's do the same thing for ADE, that triangle. Start by finding the length of the hypotenuse, measuring in millimeters. So that's going to be AD. And then we're going to find the length of the opposite side. It goes in this order: hypotenuse, opposite side, adjacent side. So hypotenuse, and then I'm going to measure the opposite side, so that's DE. And then I'm going to measure the adjacent side, and that must be AE. This is all about the setup. We got to do the setup. So I'm going to speed run it, get back to you. Like, you can skip forward in a minute, or skip forward like 20 seconds. Here goes. AD. What I measured, I did 50 millimeters. So 50. Well, that's kind of clever. 50. 50. Let's go 50. Straight up 50. Again, you can skip forward in all of this. I'm just going to kind of just measure again. DE, 30, 36, AE should also be 36. It is 36 and 36. All right, there's my table. So measuring from the table, I have DE, AE, those are both 36 millimeters, and then AD is 50 millimeters. Now, the whole point of this is that, yeah, you can measure, but we want to get some shortcuts. We want to get some tricks. And a major trick shortcut is what we get to do with those numbers. We're going to actually write out the fraction from those, and we're going to get our calculator ready to go. So I'm going to get my calculator set up on Desmos, and that way I can do the calculations, or you can use Siri and ask for some help or whatever. So here goes. The side opposite angle A, that's the green side, and we're going to divide by the hypotenuse. Then we're going to do the side adjacent to angle A, and also still divide by the hypotenuse. And then last of all, we're going to do the side opposite angle A, and then we're going to divide by the side adjacent to angle A. We're just going to write out those fractions using the numbers from up here. Color code is your friend, and it always should go, I didn't think this one through. Hypotenuse, green, yellow, red, but whatever. So we're going to do hypotenuse first and identify it, and we're just going to set up all of these fractions. So for triangle ABC, the values of the side opposite angle A divided by the hypotenuse create this fraction, 52 over 73. And I want to go get my decimal calculator ready for that. The side adjacent to angle A for the hypotenuse is this number divided by this number. It's the same setup though. And then last of all, the side opposite adjacent A and the side opposite angle A and the side adjacent to angle A would be 52 over 52. Now I'm going to keep going. For the other triangle, 36 over 50, because it's the green opposite side divided by the hypotenuse. So 36 over 50. And again, adjacent side, 36 over 50. And then last of all, 36 over 36, because it's the adjacent side. It's the opposite side divided by the adjacent side. Let's get those values. Ready? 52 divided by 73. For 52 divided by 73, I get 0.712, which is in both locations. And then 52 divided by 52 is a 1. Now we're going to do 36 divided by 50. What? Crazy. I get 0.72. See right there? You get 36 divided by 50, you get 0.72. 36 divided by 50 again is also 0.72. Oh, these are really close together in value. That's interesting. Okay, and then last of all, 36 by 36 is a 1. So there it is, right? We have this statement from Gabriel. Gabriel says the side length ratios of the opposite side to the hypotenuse are the color needed. So opposite side was green and the hypotenuse was yellow. And then the adjacent side is red to the hypotenuse is green, but they're approximately 70%. To be specific, it is square root 2. 1 divided by the square root of 2. It's actually supposed to be 0.707, so he's really close. To be more accurate, he should be at 70.7%. Because that's actually what the trig ratio should be, but we're going to save that for the later. There it is. That is the setup and the notation that we get for a 45, 45, 90 triangle. It doesn't matter how big the triangle is or how small the triangle is, the ratios of the sides in this order is always going to produce these specific values. Let's move forward a little bit. Oh, nice. Okay. So what we did in the last chapter is we talked about, or module topic, etc. We talked about when you have sides of triangles, you can make proportions and then you can solve those proportions. So I'm going to say the diagonal of this square is 60 centimeters. And if we want to find the side lengths, what we need to do is put in x and I guess the same letter because it's a 45, 45, 90, so the two sides are the same. And I can put a 45 in this corner, and I can call that theta, and then I can go theta, HOA. That tells me this. I can write the fractions for the opposite side to the hypotenuse, and I can set it equal to that decimal from what we got in the previous problem. 0.7071, and that's as far as we need to go for realistic purposes. Solve for x. Cross multiply, too much. Just multiply by 60, both sides. X equals 60 times 0.7071. X equals 42.43. Centimeters. That's that length and that one. That's what we get to do with knowing that when we have a 45, 45, 90 triangle, it helps us solve problems faster because we're not left in the dark. We have a path forward to know what our answer should be. Mina is picking oranges from the tree in her yard. She rests a 12-foot ladder against a tree at a 45-degree angle. I don't see a triangle drawn. I might as well draw the ladder. There's the ladder. It's 12 feet. We should draw the tree. Okay, the ground, and it's going to make a 45-degree angle. So once again, zooming in, theta, HOA. We are going to label theta the hypotenuse, the opposite side, and the adjacent side. And if we want to know how far is the top of the ladder from the ground, that's x. That's the unknown side that we don't know right now. We need to know it. So we can set up our fractions. We can set up the fraction of x over 12. And that x over 12 is the fraction of green over yellow. And looking back on the previous page to the previous table, green over yellow is this fraction. Well, technically, this decimal. But our measurements were really close to 0.7071. So when we're measuring in millimeters, that's pretty good. So we're going to go ahead and set this fraction equal to 0.7071, and then we're going to solve it. Cross multiply is too much. Cross multiply does more than you're supposed to. But multiply by 12. Multiply by 12. Hey Siri, what's 0.7071 times 12?
0.7071 times 12 is 8.4852.
That's how many feet above the ground her oranges are. Is 8.46. I'm rounding to 2 spaces. There you go, you guys. That is our lesson on 45, 45, 90 triangles. You should do the notes on the 30, 60, 90 triangle, but that's it. That's what we need to know. Thank you for watching this video. Thank you for getting this page done. Put it on, not just like in your bookwork, but also like write out some of the things that you observe, because I'll let you use your paper notes and maybe not the book pages on an upcoming assessment. Thanks for watching. This video is long, I know, but you went through it. I appreciate you, and I will see you in the next video.